In this video, we will learn how to draw pi molecular orbitals of allyl cation and also how to identify which one of those molecular orbitals is HOMO and which one is LUMO. Molecular orbitals are created by combining atomic orbitals, and for pi bonds, p atomic orbitals get together. Every time we see a double bond, it was created by a p atomic orbital here. And there is also another p atomic orbital here. When we have a carbocation, it is sp2 hybridized, so one s and two p orbitals were used, and that means there's one p atomic orbital here as well that was unhybridized. So anytime you see a carbocation, it has a p atomic orbital as well. So here we go, we starting with 3 p atomic orbitals, and the number of atomic orbitals that we start with has to be equal to the number of molecular orbitals that you create. So if you're starting with 3 atomic orbitals, that means we're going to make 3 new molecular orbitals. So let's go ahead and show this 3 times. I am just going to paste it 3 times, and now we have 3 new molecular orbitals. The next thing we need to do is we need to color in our atomic orbitals inside the molecular orbital. And in order to do that, we just have to realize that p atomic orbital has 2 lobes, and one will be different color than the other, representing different phases. And the way we will color our molecular orbitals is we will start by all of the colors matching. So we will go ahead and make sure that all of our colors match. And this will be the lowest energy, most stable molecular orbital. And this orbital will have 0 nodes. A node is a place where electrons cannot exist. Then we will have 1 node for the next molecular orbital and 2 nodes for the next molecular orbital after that. This is molecular orbital, we will call it psi1. For the second molecular orbital that has 1 node, we have to put a vertical line through this molecular orbital, signifying the node, and it has to be symmetrical. So since this has an odd number of atomic orbitals, we will have to put my node through the center, through this here. And every time there is a node, that means that color is changing. So for example, if I have this color, I will have this color here. Now if there is a node through my orbital, then what I will show is instead of coloring it in, we will show it as a dot. So we will show a little dot here, and then we will show the other two p orbitals, creating this psi2 molecular orbital. For psi3 molecular orbital, we have 2 nodes, so there's a node after every orbital. And again, every time there is a node, we have to switch colors. So we switch, and then we switch again. And these are the new molecular orbitals for my allyl cation. The next thing that I have to do is, in order to find HOMO and LUMO, I have to distribute my pi electrons. And a double bond has 2 pi electrons, so this will have 2 electrons to distribute. Carbocation means that it's lacking electrons, it doesn't have any. So in this particular molecule, we only have 2 electrons to distribute, and the electrons go from bottom up, from the lowest energy to the highest energy, and every molecular orbital has a maximum of 2 electrons. So we go up, down, 2, and we're done, because this molecule does not have any more electrons. Next thing that we're going to do is we will find our HOMO and LUMO. HOMO is highest occupied molecular orbital. So it's a molecular orbital that is highest and it has electrons in it. There's only one molecular orbital that has electrons in it. So this must be it. This must be my HOMO molecular orbital. The next molecular orbital is LUMO, lowest unoccupied molecular orbital. So it's an orbital that has no electrons, which is side 3 and side 2, but it has to be the lowest one. So this one, side 2, will be my LUMO.